Good afternoon. I'm Mark Everson. This is hydroponic carbon capture at source, HCCAS. We know we have ongoing carbon dioxide emission. We have far too much fossil fuel embedded and distributed throughout the infrastructure. The only extant large-scale solution, CCS, buries that CO2. It's very expensive, it poses a long-term risk, and you can only do it in a few places. The competitor, biomass, actually competes with our food. We're running out of land now to feed the people that we need to feed already. Our existing systems are increasingly destructive and short-term. We're seeing massive deforestation, biodiversity loss. We're now seeing algal bloom poisoning the oceans. One thing we do know is that crops love CO2. Can we therefore co-locate highly compact agriculture with the CO2 emitters to grow much more quickly and absorb the CO2 at the same time? I think so. Here's the scheme. Without going into detail, we can discuss this later. On your left, CO2 goes in. On your right, oxygen comes out, green stuff comes out. We're talking food, biomass, biochar. There are no other unwanted byproducts. It is fairly simple. It also has a lot of benefits. Firstly, it's extremely flexible, fully scalable, retrofit-friendly carbon capture. Any emitter anywhere in the world can be made potentially carbon neutral, possibly carbon negative. A 2-acre facility making biochar, that's about 2 American football fields, should sequester around 2.5 million tons of carbon dioxide. Not bad. It's also really efficient agriculture. It's about 90% better than the field farming per square foot. Square feet are flat. This also goes up, which means it will be vastly more effective in terms of yield. On top of that, it's pest, weed, and weather immune. It should also make money. A 2-acre facility growing spinach should turn a profit of about $1 million a year. It's non-polluting, there's no algal bloom, and it's flexible. It releases land for reforestation, and there are many other benefits too. It's non-destructive to the Earth's own systems. We're not seeding the atmosphere, we're not changing the ocean chemistry, we're simply helping nature do what nature does, only quicker. It's simple, it's low-tech, it's low-cost. It conserves water, it will even generate water. It overcomes pollution. It's 100% fail-safe. It's low risk. They're established technologies. We could do this tomorrow with what we've got today. The design is fast deployment, it's low cost, it's high density, it's plug and play, and it uses existing global infrastructure. It's a land utilization multiplier, and it will reduce hunger. We know that children learn much better when they're properly fed, and hunger is a conflict driver. We're mitigating those. That is HCCAS, and I think it actually can change the world. Thank you.
Thank you. Questions from the judges, please. Alex.
Hi, I'm Alex. So my first question is, you said we could do this tomorrow. So what would be stopping you from doing it tomorrow, and what would you need to do it?
Money.
So be more precise.
Okay.
What do you need in terms of money or land or partnerships to make this happen?
Okay. At the minute, I'm just a guy in a back bedroom with an idea. I'm not the guy that you need to make this happen. There are far better qualified engineers out there with far more recent experience than mine. I would like to see a team assembled, ideally led by someone like MIT, because you guys have the brains and the experience to put this together. I think that the theory stands up. I've done a lot of research on it. The numbers all stack up. I can take you through the numbers if you'd like me to. It honestly does seem to me to offer a solution to a major problem that we have in the world today. But I'm not the guy to do it. I'm the guy to advise on it. It's my idea. But I think that the team will need to come from somewhere like this. Does that answer your question? Okay.
Hello.
Hello.
In 1 minute, if you can go back to the slide where you had the whole flow chart and actually quickly walk through that, because I think I got all the benefits, but I still haven't got the product. In my limited knowledge, it would be really helpful.
Don't worry. We were told to focus on the what, not the how, so I hit it. Okay, that's the overall process. So the factory will produce flue gas. The flue gas contains CO2. It can be a factory, it can be a power plant, it can be anything. That CO2, the gas itself may need scrubbing. It may contain sulfur, depends on what it's actually coming from. Some natural gases won't require scrubbers. Sulfur-rich coal or coke will need scrubbing. clean the gas, then recover the heat, recover the water. That heat and water goes back into the hydroponics unit. So essentially, you're recovering whatever useful stuff you can from this. The cool, clean gas then will contain CO2, which may be in a level too high for some plants. Plants vary in their tolerance to carbon dioxide. If the levels are excessive, we simply dilute it with air to bring those levels down to the best possible level for the plants themselves. That then goes into a mass of hydroponics units. I've got a sketch designed for the hydroponic unit itself. We can take a look at that in a minute if you like. Out of the back of that, we then get oxygen released, and we get the green stuff, food, biomass, biochar. Does that?
Could you just describe a little bit more what happens in the hydroponic unit?
Yeah, sure I can. Can I just take a minute to go to the slide? I brought some additional stuff with me, just in case. Okay, putting this together, I was trying to figure out what we need to actually make this work in practice rather than just on paper. It's got to be rapidly deployable at low cost. It needs to be standardized. If it's going to go global, you can't have tens of thousands of different components all trying to work, so it should have a few bits in it. It should minimize the land area needed. It should be plug and play. We do not want very sort of highly skilled engineers being needed all over the place to do this. That took me to an ISO shipping container format. So basically something that we have an existing container handling system available worldwide. So first thing is container dimensions. You also need the maximum productive time. You don't want to be spending hours walking around inside the container, planting everything up, and hours walking around harvesting it all. And you need the greatest possible flexibility in terms of what to grow. You should be able to grow everything from watercress through to maize. That takes me to a cassette system. The cassettes will be, again, to ISO standards, so they'll be handleable by pallet trucks, by forklifts. Just thinking the numbers through, that means that if we take a four stacked containers with 4 tiers cassettes in those, you're getting 16 times better land utilization. That's the sketch of what it will actually look like. At the back end, you've got power, irrigation, nutrient going in. All of the connectors in this will be off-the-shelf plug-and-play connectors. Again, keeping the cost down, keeping the parts count down. The floor will be not a driven floor. It will be a chain or a belt within the container, but it will be powered as and when it's needed to by an externally plugged-in motor. You don't want the cost of having a motor in every container. It's just silly. The lighting is provided by LED lighting strips. Those will be hung down the sides of the container. Again, any height, depending on the number of tiers that you've got. As the cassettes plug into the container, they will make with the connectors at the back. And again, as the cassettes themselves butt together, they will make with the connectors there.
So can I stop you there
just
because just for time? So just a general question. What do you say to the multiple challenges of organizing an agricultural system, an energy system, a transportation system around something that you've clearly put a lot of thought into? All of those different challenges, which you know, can be the death knell of of a wonderful, really well-designed plan. What do you say to that?
It's been designed to utilize the tools and the systems that we've got. Transportation, containers we've got. Actually getting this thing up and built, it's not difficult. It uses off-the-shelf parts. Nothing that I'm looking for here will take a 15-year development plan. I can literally walk into B&Q and buy most of the bits that I need to actually build this. The containers will take some design work, but it's simple design work. I actually don't believe there is any major hurdle to implementing this. Does that? Okay.
I have a very basic question, and I apologize if I'm taking you back in your explanation, but one of the things which you have assumed in all this process is that you're going to have a completely clean water coming from the chemical plant and taking care of distilled water which you're going to come and mix in it. My understanding is even till today, most of the water which is coming even from our water waste management systems, cleaning supplies still are having a huge problem with various hormones present in it, various still sulfurs and chemicals present in it, which is going in water bodies underground. And I'm assuming you're mixing all those things together still with this chemical water. Like, I'm not able to understand how's that going to be taken care of.
That's okay. Remember that the water will be recovered from the vapor, which means the scrubber should be able to take out most of the toxins from that. As the water condenses out, essentially it should condense out as largely pure water. In terms of the actual application of that, we can grow food, but we can also grow biomass or biochar. If you're in an environment where you cannot clean the water that far, make biochar. It doesn't matter. Biochar doesn't care what's in it. Biomass doesn't care what's in it. If we need to limit the food only to those areas using clean fuels, we can do. It is very flexible. Does that answer your question?
Okay.
Yeah, okay, thank you.
Thank you.
Just one more question.
Please.
Sorry, thank you. So, as I understand it, what you were saying, sort of this part is really the innovation, and the scrubber part is sort of the more conventional technology.
Yeah, the scrubbers you can basically
That's
buy
what you're saying
off the
is
shelf.
off the shelf and
Yeah.
existing. So that all makes good sense. You mentioned you could scale it up in different sources of the emissions.
Yeah.
I can kind of see how it works for a large source emissions. How would it work for smaller sources?
It's a question of how far down you want to take it. It probably wouldn't be worth doing for a small bakery. But if you've got anything which is generating enough CO2, it's going to be a basic question of economics, really. We know that we need to get the CO2 levels that we're generating down. It's up to us to say, well, okay, it's worth investing this much in, that much in. The numbers will work out. The point of this one is these are container units. You can build a facility with 2 containers. You can build a facility with 2,000 containers. It's a question of space. The technology is the same. It all just bolts together. So it is fully scalable.
Thank you.
You're welcome.
Thank you.
Thank you very much.
Thank you.